Hello, in this video I want to present the first problem of the first Putnam exam, and this is hopefully the first video in a series in which I will present the solution to all the problems of the first Putnam. And for those who may not know this, the Putnam, officially the William Lowell Putnam Memorial Contest, is basically one of the hardest, if not the hardest, math contests in the world. It's open to math undergraduates registered in universities in Canada and the US. And recently, it's been all over the place. You have set theory, you have group theory, you have topology, you have many types of problems, you have analysis. But in the earliest instances of the contest, the problems would be understood by modern students of many fields, like, for example, engineering, physics, or math. They are mostly concerned with calculus, some linear algebra, a bit of other things, but they are mostly understandable by someone who's got a basic math education, who's just been studying any quantitative field. So let's get to it. So this is the problem A1. So in the Putnam exam, it's taken over a whole day, and there's a morning session and an afternoon session, and the morning sessions of problem are A1 to whatever it is. Now it's standardized, it's 6 problems in the morning, 6 in the afternoon, but in the first series it's very little. And I will not write the problems in text, I will just basically explain what the problem is. If you want the text of the problem, there is a link in the description that you can have a look at. And the idea here is that we have some volume in space, and it's bound between two planes, so z equals h over 2 and z equals minus h over 2. And the volume has a very specific characteristic in that the area of any cross-section in parallel to the xy plane is given by this third-degree polynomial in z. So basically the area of each of these sections depends on the variable z, the height along the z-axis, in a third-degree manner. And we want to prove that if you take the area at the bottom and name it B1, and the area at the top name it B2, so basically in these two planes, and the area in the middle in the xy plane as being M, we want to prove that the volume of this thing here under this condition is 1/6 of the height of the solid multiplied by b1 plus b2 plus 4m. And also, given that, we want to deduce the formulas for the volume of a cone and a sphere. So you can try the problem if you want to. If you need a hint, we can say that this is a very straightforward problem. Just basically try to calculate this and calculate the volume in some other manner and show that these things are equal. So let's get to it. Okay, so we'll start with the expression, the algebraic expression we have as the result, which is 1/6 of the height times this the sum of the area at the bases and then in the middle. We basically added these things that we call the B1, which was the area at the bottom, which is simply by plugging the z coordinate of the bottom in this formula will be equals to a times h over 2 cube plus b times h over 2. Sorry, this is a minus because this was at the bottom. Squared plus c times minus h over 2 plus d. And we had B2, which was the area at the top. Well, same thing without the minus sign. Plus B times h over 2. Whoops, it's not. To the third power squared plus c times h over 2 plus d. And now we had the area in the middle. Well, this is easy. This is with the z position equals to 0. So I will not waste space. That I will say that m is simply equals to h. And we want to calculate the expression that was given. which is equal to h over 6 times b1 plus b2 plus 4m. Well, we can simply add these things. It's a bit of algebra. We notice here that the terms with odd powers have the same argument, but with different signs. So when we will add them, we will add this thing here, we'll get the minus sign to the third will come in front. So we can take the sign here and put it here. And when we add these things, they will cancel out. And the same thing happened with these terms here. So when we calculate b plus 2, we will get twice this term. And because here the minus sign will disappear before the square, and we have the d's which will add to each other. So this is simply equal to h over 6 times, let's see, b plus b, this will be 2b, and there's this h squared over 4, because the 2 squared is, and the 2 squared is 4, and we add these two terms would be plus 2d, and we add this 4m term which will be, oh, I said m equal h, sorry, m is equal to d, of course, plus 4d. And a bit of algebra, we'll see that these 6's will cancel each other, so it's hd plus, here we have 2 over 24, which is 1 over 12, and we have bh to the third. So this is the first result we get, and we want to prove that this is equal to the volume of our solid, which we'll calculate on the next board, so I will reproduce this result. Okay, so we calculated the volume using the formula we wanted to prove, with the b1s, b2s, and m, and now we're trying to calculate the volume in another manner. We want to prove that this is equal to this expression. So obviously, what we want to do is we're going to use the slice technique, in which we basically will integrate the area of each cross-section of the volume multiplied by a small height element. We'll sum these up, and this will give us the volume. So here the volume is equal to the integral of a of z dz, and we integrate from z equals minus h over 2 to z equals h over 2. So it's really straightforward calculation. H over 2 to h over 2. And a of z is given by this polynomial. So now we have 4 terms, but just as we had previously some terms were cancelling out, we see that we are integrating over an interval that is symmetrical about the origin. And we are integrating some even functions and odd functions. So the odd functions, basically an odd function is a function that will be anti-symmetrical with respect to the origin. So if we have a function that goes like this, and here we have a function that goes like this, when you take the integral over this interval, these things will be negative, and it will be exactly cancelled out by these terms here, which are positive. So we have a negative area plus a positive area, and these will cancel out exactly. So we don't have to take into account the z cube and the z term. We just have to take into account these two terms. So the volume would be equal to the integral of minus h over 2 to h over 2 of b z squared plus d dz. Now, when we integrate z squared, we will get z cube over 3. So this is equal to b z to the cube over 3 plus, then we'll just d to just become the constant term will become d times z. And we go from minus h over 2 to h over 2. And we just plug this in, so we will get h cubed over 8, and then minus h cubed over 8 when we plug the minus here. So this will give us b times h cubed over 3 times 8, and the z will be plus h over 2 minus, well, the same thing with the other limit of integration, b times minus h over 2 cube minus h over 2. And when all is said and done, we have these terms, h over 2 minus h over 2, which give us, what is it, d, sorry, here, would give us d times h. And these terms here, bh cubed over 24 minus bh cubed over 24, the 2 to the cube would become 8, will give us 1 over 24 plus 1 over 12, which is 1 over 12. So we will get the result plus b h cubed over 12. And of course, we see that these two expressions are identical, which prove the first part of the problem. Now what we will do in the second part, we will use this formula. So instead of having to do an integral, which we don't want to do each and every time, we will we'll use this formula, which is simply algebra, to try to get the volume of a cone and a sphere. So we'll get to the cone on the next board. Okay, so now we have the volume of a cone of height h, and remember our setup, the solid had to be bound between two planes that were separated by the distance h, was symmetrical about the origin. So we have our cone here, and of course we will have the cone. And if we want to have a coordinate system, this will be equal to h over 2. The z coordinate of this one is minus h over 2. And we remember our setup required that the area as a function of height over the solid was given by a third degree polynomial at most. And here, well, we know in a cone that the radius of the cone is will go as the height, the distance over, sorry, not the height, but the distance z over the z-axis. That's basically the definition of a cone. You take a straight line and you turn it up, so the radius will be linear in z. There may be an offset here, but we don't really care. All I want to do here is to prove that we can use the theorem. And the area here of this thing here, of any section, will be proportional to r squared, and this is proportional to z squared. Plus maybe a constant, we don't care about it. What we want to know is that the degree of the polynomial is a degree 2, and we satisfy the conditions of the theorem we just proved. Our theorem gave that the volume, I kept the wrong result here, it's not very useful, is equal to h over 6 times b1 plus b2 plus 4m. And remember, b1 was the area at the bottom, b2 was the area at the top, and 4 was the m was the area in the middle. Now, using this expression, we have the volume is equal to, well, the height of the cone here, which is h over 6. Now, the area at the base, if we have a cone of radius r, the area at the bottom is pi r squared. Then we need to add the area at the top. Well, at the top we're at the apex of the cone, so the area is 0. Plus 4 times the area in the middle. In the middle, the radius here is equal to half of the radius at the bottom, because that's a cone. Basically, when we halfway up, the radius is reduced by a factor of 2. So we have plus the tower times pi I over 2 squared. And this gives us, which is h over 6 times these 2 squared and this 4 will cancel out. So we get 2 pi r squared. Which is equal to h pi r squared over 3, which is the usual formula for the volume of a cone. And the next board will do the evaluation for a sphere. Okay, so we are back to our basic setup. We have some coordinate system and we have a sphere here. And the sphere has a radius here of h over 2 because it goes by between minus h over 2 and h over 2 in the z direction. And the first thing is to make sure that we can use our theorem is that we have to know that the area at any point on the sphere is according to a polynomial of a degree most 3 in z. And here, of course, we know that the radius of the sphere squared is equal to x squared plus y squared plus z squared, which means that any circle here at a given z height satisfies the equation x squared plus y squared equals I squared plus minus z squared. And we know that the area here of this circle, this is like the radius of the circle. So the area will be proportional to the radius squared, like the area of a circle is pi r squared. If this is equivalent to the radius, then the area will be proportional to r squared minus z squared, which is a polynomial that is of degree 2 here. It's got one term in the z squared and one constant term. So we satisfy the theorem and we can just use these things to try to calculate the value of the volume of the sphere. And we just plug these things in there. So v is equal to h is equals to twice the radius, 2r over 6. And here it's very easy because the area at the bottom and the area at the top are basically 0 because we are at the top and bottom of the sphere. There's nothing left here. So these terms will be 0. So it's 0 plus 0 plus 4 times, well, the area here is in the middle is, this is a circle of radius h over 2. So it's pi times h over 2 squared. Okay, so things will cancel out, but we want things in terms of radius and not h over 2. So what we can do is that h over 2 can be replaced by the radius r, which is the radius of our sphere. So this is equal to 4 times 2, that's 8 over 6. There will be a pi, and the r squared is multiplied by the r here is a r cubed, which is equal to 4/3 pi r squared, as usual. And that's it for today.